we're going to see there's another conflict in rules coming. The first conflict we encountered was that opposites attract, similars repel, and the structure of the atom shows that protons lump up in the nucleus and electrons stay away. These are in direct conflict with each other. Live with it. Scientists had to live with it for like 20 years before they figured out the answer. This resolution we will discover a little bit later. But I want you to think about how you could make those two rules work. What does it tell you is required to make this conflict go away? The second conflict we're going to solve first. Atoms must be neutral, and a second rule was discovered in nature that atoms must have complete valence shells. That is, the shell should be totally full or completely empty. There should not be partial valence shells. And we will see this resolution on Friday. Let's look at what this means. Here are three elements, 9, 10, and 11. All of them are neutral. Each of them has 9 protons and 9 electrons, 10 protons and 10 electrons, 11 protons and 11 electrons. And the neutrons are irrelevant to chemistry. I did not draw the nucleus in. I didn't want to complexify this more than necessary. If we look at these diagrams, my Collotti notation of giving you more shells than necessary can cause a little bit of confusion. It simplifies many things, but here I want to remove my spare shells. Now you've got a better look at it. Fluorine is missing a soldier. Sodium has got one soldier in the outer wall, and fluorine is perfect. This little bear had too much, this little bowl had too little, and this one was just right. Now, if you were on a castle, you would probably go, dudes, the enemy's going to attack here. So you'd probably want to fill that spot. And this soldier out here is like, this frickin' sucks! How come I get to defend the entire outer wall? By myself! But the real key to this is when you see it in grade 11 and 12 and you start studying the wave model, and neon looks like a beautiful flower that's completely done. And fluorine looks like a flower where someone yanked off one of the petals, and sodium looks like a flower where someone plucked off the entire outer row but one. And you can see it's like begging to be finished. Neon, though, just sits there going, I'm totally complete. 10 protons, 10 electrons, and I got complete shells. And fluorine is like, oh yeah? Oh yeah? Huh? What's fluorine going to do? Fluorine's going to come and say, like, there, see? I found an electron. I'm complete on the outer shell now. Yeah! And Neon goes, you stupid loser. Now you have 10 electrons and 9 protons. You screwed up rule 1. And fluorine is like, Neon, that sucks. But it did it. But it's unable to complete both rules at the same time. Sodium kicks away that one electron and goes, nah, 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 nah. Now I have a complete outer shell. And you might go, but it's not there. Yeah, it exposed the shell just inside to be complete. It's like peeling off a damaged. You're going to turn your attention to charge. Onion layer and showing a complete onion underneath. But this has led them to screw up rule 1. Fluorine picked up an electron, so it now definitely has a charge of -1. It's unbalanced.
You're unbalanced.
And sodium threw away an electron to become +1. And this sometimes causes students confusion. So let's look at that graphically. Here's a neutral atom at the bottom. Equal number of protons and electrons. So if you add up 11 negatives and 11 positives, -1 plus 1, it's 0. I take away one of these electrons. Come on, subtract yourself. It's not working. Where's it gone? If I erase one, it just keeps disappearing. There's supposed to be a little box that erases this. If I scrub off this one electron here, then there's a lone proton who has no date. Cancel, 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 cancel. Cancel and Gretel! We cancel here, but if this guy was taken away, nobody cancels the positive, and he's positive 1. So what do we do when we draw all our Lewis dots? Well, you're not going to see this. The empty shell should expose a full shell underneath. You see a Lewis dot diagram like this, and you go, well, throw this one out, and it's taken care of. Throw away a negative, you're positive 1. You'd still go, this is more empty than full. Throw away 2 of them. You get positive 2. Now you got 3, and you go, whoa, do I throw away 3 or get 5? Easier to go 1, 2, 3. Toss away 3, you become positive 3. Now you're like, what do I do? What do I do? Gain 4, lose 4, And that's exactly what this element's going to do. It's going, I don't know what to do. Should I gain 4, lose 4? And the end result is it does a tremendous number of like seriously kind of almost like bipolar behavior. And so write nothing for these halfway point ones. That would be carbon and the ones underneath it. But by the time you reach 5 electrons in the valence shell, now you go, oh, I just need 3 more. If you pick up 3, you become minus 3. If you pick up 2, you become minus 2. Or the way I like to think of this one is it's missing 2, minus 2. Missing 1 would make it minus 1. La! This one's done. You need nothing. So the trick is at the full point or the halfway point, you write nothing. Plus 1, plus 2, plus 3, minus 3, minus 2, minus 1, do nothing. Once again, if you don't have your textbook at home, any periodic table will do, and you can look up Nelson online. I'll repost the link onto the classroom. Here is the full table of the elements that you will be working with in science for the next few years. The entries in blue are metals, the entries in red are nonmetals, and the green ones in here are called metalloids, which means metal-like. I like to call them semiconductors since these ones here are key to your solar cells, computers, cell phones to work. All of these things have a key, and it's so easy to skip reading these and then you get stuck emailing me and waiting hours or days for a response when if you give yourself some time, spend a few moments looking over something, not in a panic going, I need to answer this right now. Give yourself a moment to absorb it a little bit. These are organized by atomic number. 1 proton, 2 proton, 3, 4, 5, 6, 7, 8, 9, 10 protons. That's what this little number is up top. Atomic number will give you proton count and electron count. The lower number is the entire mass of the nucleus. And sometimes the mass of the nucleus is nice. Helium has 2 protons. Its nucleus has a mass of 4. So there's 2 neutrons in it. Radon, 86 protons and a mass of 222. So what's that? 100, 114, 126 more particles needed to reach that mass. So radon has 126 neutrons. The fractional counts we'll do at the end of the unit. It's really cool. Let's zoom in to a section of the table. I've dragged aluminum all the way over. So you see what I'm doing here? I'm taking this section between the goalposts and I'm going to drag it all the way over here so we can look at it together. Look at these little charge numbers at the top. This is the answer to your assignment. That means there's 1 electron in the valence shell. Doesn't mean 1 electron in the whole atom. There are 3 protons and 3 electrons. This just means the Lewis dot will only show 1. So this is really the Bohr diagram's information here. There's your Lewis dot. Lithium has 1 dot, magnesium has 2, scandium has 3. So would aluminum, the part I dragged over in the other table. Silicon will have 4 electrons in its outer shell. 2 and 8 make 10. 4 more makes 14. Why does silicon not show a charge? Because aluminum shows a charge of +3 because it only had 3 electrons in the outer shell out of 8, so it threw them away to make its outer shell perfect. Silicon is sitting at the halfway point. Should it gain 4 electrons or lose 4? And it does nothing that we can study in grade 9, and that's why its entry is blank. But phosphorus has 5 electrons in its outer shell. How would you know that? Well, it's telling you right there. Why 5? 2 and 8 and 5 make 15. So it's missing 3. So missing 3, it will gain 3, -3. Missing 2, missing 1, missing none. So that's all you need to do with your halfway point ones and far right ones on your Bohr-to-Lewis-Dot-Diagram assignment is enter dashes. And if you are correct, when you got to scandium or calcium, when you drew calcium, it should have had 2 dots in its outer shell. So it will throw those 2 electrons away and become +2. So that's how you can read this table and actually discover that you didn't need to do any of the work I did for you. It's all in the table. But unless you understand what these entries are for, you can't work with them yet. And it turns out each row on this table is one of those electron shells. Orbit 1 has 2 possible electron positions. Orbit 2 has 8 possible electrons. Orbit 3 has 8. Orbit 4 has 18. But watch, you see 2 and 6? If I count these 2 and these 6, there's the 8. These ones from column 3 to 12 have been isolated because they're following a different rule. And that's what you'll get to in grade 11. So we still have 8, 8, and actually 8. See? 1, 2, 3, 4, 5, 6, 7, 8. All right, why did I say 5? It has 5, it's missing 3. It has 6, it's missing 2. So the structure of 8 per orbit actually holds if you completely remove this block in here. Then you actually have 8 entries per orbit. But we'll get to that later. So if you are correct, when you drew fluorine, it should be missing 1. When you drew argon, it should be missing none. When you drew phosphorus, it should be missing 3. And that's how you can confirm with the table that you did your drawing correctly.
Look at you. The deed split your spirit to the bone. You were unbalanced, bested by a girl who had never held a lightsaber. You failed! Skywalker!